And in the afternoon, our first speaker is Professor Fan Yingying. And the title of the talk is Asymptotic Properties of High-Dimensional Random Forests. Professor Fan Yingying is a Centennial Chair in Business Administration and Professor in Data Science and Operation Department of the Marshall School of Business at USC. She received her PhD in OR and FE from Princeton University in 2007. She taught statistics at Harvard and was the Dean's Associate Professor in Business Administration at USC. Her research interests include statistics, data science, machine learning, economics, big data, and business applications. Her latest works have focused on statistical inferences for networks and AI models, empowered by random matrix theory and statistical learning theory. She has won many important awards and honors, including but not limited to the recipient of the Institute of Mathematical Statistics Medallion Lecture, the International Congress of Chinese Mathematicians 45-minute invited lecture. She's also NSF Faculty Early Career Development Award receiver, the Royal Statistical Society Guide Medal in Bronze. She's a fellow of IMS, ASA, and fellow of American Statistical Association. She has served as associate editor of the Annals of Statistics, Information and Inference, Journal of American Statistical Association, Journal of Econometrics, the Econometrics Journal, and the Journal of Multivariate Analysis. So without further ado, let's welcome Professor Fan Yingying. Professor Fan, please.
Thank you very much for the very generous introduction. Let me share my screen first. Can you see my screen? Okay, excellent. Let me make it a full screen. Oh, all right. All right. Okay. All right. So first of all, I would like to thank Joe and the CTU for organizing this excellent event. It is a truly great pleasure for me to share with everyone my recent work on random forest learning. The talk of my title is slightly different from what was in the program book, because I added some very recent work that we just finished about random forest. Okay. So let me first talk about the outline of my talk today. I will start with a random forest review, just in case that some audiences here are not very familiar with the random forest algorithm. After that, I will focus on two main results. The first one is on high-dimensional random forest consistency rates. I will also talk about a new condition, which we call sufficient impurity decrease condition. Because of this new condition that we introduced to the literature, we were able to get the high-dimensional random forest consistency rate. After that, I will move to random forest inference. I will focus on p-value calculation. We have power analysis as well, but because of the time constraint, I will skip the power analysis. And I should also mention that this is a joint work with Dr. Jianming Qi, who was a joint postdoc of myself and Professor Jingqi Lu, and Patrick Wasler, who was a PhD student at USC, and my colleague, Professor Jingqi Lu at USC. And the results in my talk can be found in these two manuscripts, both of them are available on arXiv. All right, so let me start with model setting. So in our work, we consider non-parametric regression model. We have the observations from this non-parametric regression model, where the covariates are p-dimensional, and in p-dimensional hypercube. And this p, we consider the high-dimensional case, where p can be very large, even much larger than sample size m. And for the covariates, we assume that they have a joint density, and density is bounded away from 0 and infinity on the domain. And for the model error, we assume that the Q's moment is finite, where Q is some large enough value. And the regression function is bounded on the support. And throughout my talk, I will make these regularity conditions without explicitly mentioning them. All right, so then let's look at the random forest algorithm, and I will give a very, very high-level review of it. So random forest is a ensemble algorithm. It integrates a lot of tree estimates to form a final random forest estimates. And the word random refers to two sources of randomness in forming the final estimate. So in my talk, I will focus on the column subsampling. This means that we have p covariates. But instead of using all p covariate, we will consider a subset of it. And the size of the subset is usually gamma 0 times p. Gamma 0 means proportion of covariates. So we pick from all available covariates. Random forest random forest build trees by recursive by partitioning. It starts with a root cell, which is the entire domain of the covariates. And then it finds a covariate J1 to split on, as well as a location C1. So it splits allocation C1 along covariate J1, and the entire cell, root cell, becomes two subcells. Okay, and I should mention that here we focus our attention on covariates just in the column subset. Recall that this is the subset of all available covariates, and we search which one to split on according to some criterion, which I will mention in a few slides. After you get the two daughter cells, you repeat the process and split again. Then you get the next level of cells. So in this diagram here, we have a decision tree of height 3. You can also call it a level 2. So at the end level, we have 4 cells. And if you look at the process, the end level, the 4 cells form a partition of the entire domain. Once you have the partition, you can form a tree estimate. This tree estimate means if I want to estimate the value of my mean regression function at a given test point C, what I do is I look at in which end cell the point C falls into. Then I use the average of the responses of the data points in that cell as my final estimate. So this is a mathematical notation on the simple factor I just mentioned. So this is an estimate formed by one tree. But recall that when I talk about how we build a tree, I mentioned the column subsampling, right? So at each time when we build a tree, we have along each split, we have a column subset. So you can imagine there are different combinations of column subsets. Then for each combination of column subset, it is likely that I will get a different tree. Right? So at the end, I will have a lot of trees built, each corresponding to a combination of column subsets. So in random forest, the final estimate is aggregation of all this tree estimate. And in our study, we consider random forest formed by all possible trees, obtained by all possible column subsets combination. And for each column subset, the size is fixed and is controlled by a parameter gamma 0, which falls between 0 and 1. And in random forest algorithm, our package random forest algorithm, the default value of gamma 0 is 1/3, although this number has never been theoretically verified to be optimal. But nevertheless, it performs very well in practice with 1/3. We make the assumption that the column subsets, all these column subsets, they are ID and uniformly distributed over all possible column subsets combinations. So the number of all these column subsets can actually be explicitly written down. And now we are ready to build a random forest estimate. Since in the random forest, we have a lot of trees, each tree forms a partition of the entire domain. At the end, what you do is you average all the tree estimates to form a forest estimate. Here in this diagram, the point of interest C falls into this cell. So it corresponds to the cell here in the partition formed by the N cell. And for the second tree, it falls into this cell here. And for the third tree, it falls into this cell. So at the end, what you do is you average all these tree estimates and you get a forest estimate. And this is indeed a shorthand notation for what I just mentioned. It's a simple average of all tree estimates. And for people who are familiar with random forests, know that there is another dimension of subsampling, which is the row subsampling, or you can call it a bootstrap. So row subsampling focuses on randomly subsample a subset of observations instead of features. Our paper indeed consider the row subsampling as well, but for my talk today, I will not focus on it. So that was a very high level idea on how we build the random forest estimate. But I haven't talked about how we split the cell every time when we build a tree, right? So now let's look at the theoretical card splitting criterion, which is a criterion proposed by Breiman 2001 paper. Suppose you are standing at a cell T and you want to search for which coordinate J to split down and location C. So what you do is you minimize this criterion here. This criteria is a weighted summation of conditional variance. It looks very complicated, but indeed it has very simple intuitive explanation. To understand it, first note that the conditional variance here means I'm standing at a cell T and I use the step function constant times the indicator function on cell T to approximate my target function. Okay, and this is obvious if you expand out using the squared expectation formula of conditional variance. Once we understand this, the entire criterion here, objective function here, can be interpreted as when we move to the two daughter cells, we can use a refined step function, which takes value C1 on this daughter cell, value C2 on this daughter cell to approximate your target function. So in other words, my objective function here is conditional approximation error when we use a refined step function to approximate my target function. Okay, then with this intuition, it means theoretical card splitting criterion try to find a coordinate J and a location C such that the conditional approximation error is minimized when I move from here to here. Okay. All right. So theoretical card splitting criterion depends on population distribution. So obviously it's not available in practice, right? So in random forest algorithm, what we do is we estimate all the previous population quantities by using their sample counterparts. This gives us the sample card splitting criterion. Again, the formula looks complicated, but it is indeed a sample version of the previous theoretical card criterion. Okay, so now I hope that you have an idea on how random forest estimate the mean regression function mx at a given test point. The first goal of our study is to establish the consistency rate of random forest using tree growing rule, which we denote by T hat, associated with a sample card splitting criterion. Mathematically, this corresponds to we want to bound this squared loss. And let me walk you through this squared this target function we want to bound. Mx is my estimation target, and x is the test point of interest. And the second part is a shorthand notation for random forest estimate. I just talked about. And the loss function we consider is the square loss, where the expectation is taken with respect to both the test point and the training point where you use to build your random forest. Okay, and this is indeed a very challenging problem. Well, there is limited results, theoretical results available on random forest consistency. despite that, random forest was proposed more than 20 years ago. And the main challenge is caused by the very strong dependency of the random forest estimate on your sample, on your training sample. Recall that every time when we split, we use the entire training sample. And I also want to mention that although limited results available, there are indeed some very nice work showing that in fixed dimensional setting and with additive regression model assumption of MX, as well as independent covariance assumption, Scornet et al. 2015 paper indeed showed that random forest can be consistent, but they did not provide any consistency rate. And for our study, we want to push a result one step forward. We want to consider high dimensional random forest with sample car splitting criteria. We also want to relax the assumption on the regression function. We want to allow non-additive regression function and possible dependent covariance. So this additional ambitious goals makes the theoretical study even more challenging. So you may curious then how did we derive our result, right? So we introduced a new assumption, which is called the sufficient impurity decrease assumption. And this is a key innovation of our approach. With this assumption, we were able to derive the consistency rate. So let me first talk about the assumption, and then I will show the formal result. So this assumption says, again, this is the same diagram as before. You standard cell T, you want to find the J and the C to split to get your two daughter cells. And our condition says every time when we move from cell T to its two daughter cells, the amount of approximation error decrease. Recall that this is the approximation error decrease. If you search over all possible covariates, not just the ones in your column subset, and all possible location, it should be lower bounded by 1 over alpha 1 of your remaining approximation error. And here, this alpha 1 is it's not a constant. It's something that depends on your model. And in our paper, we have very detailed analysis on sufficient impurity decrease this condition. We indeed verified that a lot of models, including additive models with some smoothness assumption, satisfy this sufficient impurity decrease condition. And additional examples include polynomial regression model and interaction models. But because of time constraint, I will not talk about it in my slide. If you are interested in the result, I suggest you look at our paper. And in those models, this alpha 1 depends on the model setting. Specifically, it depends on the sparsity parameter of your regression model. For instance, in additive regression model, alpha 1 usually scales linearly with a number of important covariates in your regression model. All right, so with the assistance of the sufficient impurity decrease condition, we were able to show that in high dimensional setting where your dimension can increase polynomially with sample size, the random forest estimation error can be upper bounded by 3 terms. The first term corresponds to estimation bias, and this term holds for all tree depths K. Here K means the depth of trees in your forest. And it holds for all tree depths, which is upper bounded by log n up to some constant factor. And the remaining 2 terms, they are related to estimation variance, and they have polynomial order. Since the tree height is at most a logarithmic factor of sample size, you can see that the bias is indeed upper bounded by polynomial order of sample size as well. So combining this result, we obtain that high dimensional random forest can be consistent with polynomial consistency rate. Okay. And I want to mention that this is indeed the very first polynomial consistency rate under very general model setting in high dimensional case of a random forest with the sample card splitting criterion. I keep mentioning sample color splitting criterion because this is indeed the most challenging part. And there are some existing results that consistency rate, but for much simplified version of random forest, we simplify the splitting criterion. But with respect to the sample color splitting criterion, our work is indeed the very first one on the polynomial consistency rate. All right, so that was a quick summary of the first part of our work. In short, we derived the polynomial consistency rate of random forest in high-dimensional setting. Then here comes the second part of my talk. Since we understand that it can be consistent with polynomial rate, can we do some inference with random forest? In particular, can we identify most important features for predicting response variable y using your high-dimensional feature vector? This is an important question because so nowadays when we do scientific research, we are interested in not just a prediction. In a lot of cases, we are also interested in understanding like inference, for instance, interpretability of the results, right? So selecting most relevant features can help us increase the interpretability of our model. Before I talk about how we solve the problem, I want to show you some existing results. Because random forest has been popularly used for over 20 years, right? There are a lot of measures proposed for evaluating the importance of features in random forest regression. And indeed, here are listed three most popularly used measures. The first one is called mean decrease in impurity. The second one is mean decrease in accuracy. And the third one is conditional permutation importance. So let me walk you through the table. So in this table, we conducted a simulation study where we have a high-dimensional feature vector, and X1 and X21, both of them, they are important features in predicting response. But we also have many other unimportant features, which we call null features. In particular, X12 is a null feature. It is unimportant, but it is correlated with another important feature. Ideally, feature importance measure should rank X12 much lower than X1, either X1 or X21. And this table shows the fraction of times each of the three popularly used measures rank this null feature higher than either of these two important features. And in the first row, we consider low-dimensional setting, low dimension, but dimension is still 200, with moderate correlation. As you can see, with low correlation indeed. As you can see, when correlation is low and dimension is low, all three measures perform reasonably well. Only about less than 10% of the time, they rank null feature higher than single feature. However, when you move to high dimensional setting and higher feature dependence, you can see that they all start performing very poorly. So this motivates our study. How do we design a measure which performs better with feature correlation, right? And we approach this problem by formulating it as hypothesis testing. And we want to test whether feature Xj is conditionally independent of response given all other features. So the question is, how do we design such test, right? And I want to mention that the reason we formulate it as hypothesis testing because it allows us to study it in a mathematically rigorous way with theoretical guarantee, which gives us more confidence on the performance of our feature importance measure in practice. So we design our feature importance measure based on a very simple intuition. So let's first look at this statistic. In this statistic, we define Ri as a residual when we run a regression with the J's feature removed. So here, notice that we use the true mean regression function. So this is really intuitive understandings that are practically usable. So under the null hypothesis, under null hypothesis that the J's feature is not important, you can see that this test statistic is asymptotically standard normal. And then you may curious, can we design a test based on this intuition, right? The naive idea is you replace your residual with a random forest fitted residual. And then you check whether this test statistic follows standard normal distribution. If yes, then it's evidence that the J's feature is not important. Otherwise, it's evidence against the null hypothesis, right? It sounds very simple and reasonable, right? But unfortunately, this idea does not work. It does not work because of two reasons. The first reason is when you fit a random forest regression, you have the approximation error. And we know that random forest estimate converges at polynomial rate. However, it's not fast enough. So that error gives you bias. The additional error comes from the correlation among features. Okay. So we need bias correction. And to make my argument more convincing, let's look at some simulation study. So here I present the QQ plot, Q-norm plot of our test statistic in two different settings. So in first setting, there doesn't exist any feature correlation. So our features are independent. Then we use a basic test designed based on the intuition I just mentioned. You can see that it follows standard normal distribution pretty well. In the second setting, we increase the feature dependence. Here we have moderate correlation. You can see that the deviation, now the test statistic deviates a lot from standard normal distribution. So a test is no longer useful. In the third one, we conducted the bias correction using our idea, and you can see that now it's much closer to normal distribution, even in moderate correlation case. Okay, so let me talk about details on how we conducted the bias correction. So let me start with the very basic version of the test, which we call factor test. And the basic test is designed based on the intuition I just mentioned. So it literally mimics the intuition I just mentioned. Here, this is a random forest estimate with the J's feature removed. And the second part, this G function is arbitrary transformation function picked by user. And this is usually used to boost the power of it. So for this basic test, we also assume that there is an independent training sample of much larger size unavailable. And for the basic test, we show that if the bias, bias is defined by this quantity here, it's basically the expected value, conditional expectation of the numerator. If the bias is 0, and under null hypothesis and some regularity conditions, our test statistic can have this non-asymptotic upper bound on its CDF. So you can see that it's very close to standard normal. Okay? This is standard normal CDF. But for this test to be useful, you need this very strong assumption that the bias is asymptotic, is almost surely 0, which is very strong in practice. So what we do is the first idea we tried imbalancing idea. This idea says that if you are lucky enough, you have a much larger training sample, which is larger than your inference sample used to construct your test, and use a training sample to construct the random forest estimate, then you can get an upper bound without the 0 bias assumption. And you can see that now we require, in order for asymptotic normality to hold, we require this term to vanish. And corresponding requires that the training sample size for random forest is very large, much larger than your inference sample size. So that was the first idea, imbalancing sample. The second idea is conditioning. Instead of using imbalancing sample, we replace the average of all this G with a random forest estimate of G hat. And this way we can have another test statistic. And we were able to show that we do not need a asymptotic bias 0 assumption. Instead, we only need that the product of the two random forest fitting, this one and this one, they are small enough. So this is much relaxed than the previous condition. And both of these ideas are for bias reduction, but how about power? For power improvement, we use the ensemble idea. And I have a diagram here which best describes the ensemble idea. For this idea, we assume we have two independent samples. One used to train a random forest estimate. The other one is used to form your test statistic. We partition the inference sample into Kn part, and then for each one, we can form a test statistic. So at the end, we take a maximum of all these tests to boost the power. Okay, because of time constraint, I will skip this result and just mention that. Using all these ideas, meaning that we used imbalancing, we used the conditioning, and we used the ensemble idea, we can form a random forest feature importance test, and which gives us this valid Q-norm plot of our test statistic. Okay, and in my very last slide, I want to show you the same table, but with the performance of our new test added here. You can see that in the same identical setting, our new performance measure performs uniformly well under all settings, even in very high dimensional setting with high correlation among features. Okay. All right. So here is a summary of my presentation today. So I basically covered two results. The first result is on high dimensional random forest consistency. The second result is we proposed a new test statistic which can be used to evaluate the feature importance in random forest regression. It is robust to featuring correlation and high dimensionality. All right, that's my talk. Thank you.
Thank you very much, Professor Fan. It's a very impressive work. The talk is excellent. So we are a little bit running behind the schedule. So let me ask a quick question. So for audiences and students and researchers, if they are looking for the technical details, where should we find your paper?
So both manuscripts are available on my websites, and they are also available on archive.
Okay. All right. Thank you very much one more time. Thanks.
Thank you.